Good morning, everyone, and welcome to our physics class. So, I am Jaya Therese Kumonot, a best ed second year science student of JRM SU Dipolog, and today I am going to discuss to you a topic on moving charges and magnetic field, as well as the magnetic force on a moving charge. But first, let me introduce to you first the learning objectives for this topic. So, at the end of this lesson, you should be able to A. Define magnetic field, moving charge, and a magnetic force. Determine how charges move in a magnetic field with a magnetic force. And C. Use and apply Lorentz force law and a right-hand rule in solving for the magnetic forces. And now let's move on to the discussion. So what is a magnetic field? A magnetic field is the region around a magnetic material or a moving electric charge within which the force of magnetism acts. So the unit for magnetic field is called Tesla. And now we're going to talk a brief history of magnetic field. The one in the picture is Petros Peregrinus de Maricourt. The research on the magnetic field began in 1269 when he mapped out the magnetic field on the surface of a spherical magnet using iron needles. He noticed that the resulting field lines cross at 2 points. He named these points called poles. After this observation, he stated that magnets always have north and south poles, irrespective of how finely one slices them. Next, we have William Gilbert. 3 centuries later, William Gilbert stated that Earth is a magnet. In 1750, John Mitchell, an English clergyman and philosopher, stated that magnetic poles attract and repel each other. Next, we have Charles Augustin de Coulomb. This one. In 1785, he experimentally verified Earth's magnetic field. Next, we have Hans Christian Ørsted. This one. In 1819, he discovered that an electric current creates a magnetic field around it. Next, we have Henri-Marie Ampère. In 1825, Henri-Marie Ampère proposed a model of magnetism where this force was due to perpetually flowing loops of current instead of the dipoles of magnetic charge. Next, we have Michael Faraday. In 1831, Michael Faraday showed that changing a magnetic field generates an electric field. In effect, he discovered electromagnetic induction. And the last one, we have James Clerk Maxwell. Between 1861 and 1865, James Clerk Maxwell published theories on electricity and magnetism, and it was known as the Maxwell's equation. This equation described the relationship between electricity and magnetism. So take a look at this picture. This is a bar magnet. A bar magnet has the north and the south poles. And according to Coulomb's law, unlike poles attract, unlike poles repel. Magnetic field lines. So, magnetic field lines can be defined as curved lines used to represent a magnetic field. So, as you can see in the picture, these curved lines represent the magnetic field lines. They describe the direction of the magnetic force on a north monopole at a given position. So, based on this picture, it shows that always the north will point to the south. So this is how it looks like. This is showing the magnetic field lines of a bar magnet. Take a look at this first picture. The magnetic field lines start at North Pole, the red one, and ends at the South Pole. As you move away from the magnet, the field lines are farther apart, indicating the weaker field. Consider this second picture. Closer to the magnet, we can more clearly see how the field lines always start at North Poles and end at South Pole. Next, this figure, this one, shows the magnetic field lines of the attraction of opposing poles. So we have opposing poles here, the North Pole and the South Pole. The field lines will still start at a North Pole and end at a South Pole. So as you can see, the direction of the field lines goes from North Pole to the South Pole. Consider this last picture. This figure shows the magnetic field lines of the same poles called the North Poles and the South Poles. As you can see, they repel to each other. So now let's move on to the moving charge and magnetic field. So what is a moving charge? A moving charge is the amount of charge that passes a fixed point in a given period of time. It is also known as electricity or electric current, as the current itself means movement of particles in a large amount. A moving charge generates magnetic field in its environment that imposes a force on the moving charge. When charges are sitting still, they are unaffected by magnetic fields, but as soon as they start to move, the magnetic field pushes on them. So next, we're going to define magnetic force. What is a magnetic force? So, a magnetic force refers to the attraction or repulsion that arises between electrically charged particles because of their motion. It is the basic force responsible for such effects as the action of electric motors and the attraction of magnets. So what is a Lorentz force? A Lorentz force is the force exerted in a charged particle not moving with velocity v through an electric field E and magnetic field B. So, a magnetic force, or as expressed in Lorentz force law, it can be expressed using the equation F is equal to QV times B, where Q is the charge, V is the velocity, B is the magnetic field, and F is the magnetic force. So the implications of this expression include the following. 1. The force is perpendicular to both velocity v of the charge q and magnetic field B. So, take a look at this graph. The magnetic force F is perpendicular to the velocity v. Next, the magnitude of the force is F is equal to QVP sine theta, where theta is the angle of 180 degrees between the velocity and the magnetic field. This implies that the magnetic force on a stationary charge or a charge moving parallel to the magnetic field is 0. The direction of the force is given by the right-hand rule. That is the last implication of the expression. Take note that Lorentz force law is using this equation, F is equal to Q times V times B, where again, Q is the electric charge, V is the velocity, and B is the magnetic field. And of course, that arrow above is called or is showing the direction of a certain variable. So here, that will be the formula of the Lorentz force law. When the magnetic force relationship is applied to a current carrying wire, the right-hand rule may be used to determine the direction of force on the wire. So this is right-hand rule. It shows here the current, the magnetic field, and the magnetic force. So what is a right-hand rule? Right-hand rule, it is a hand mnemonic used in physics to remember the direction of magnetic forces. So, when we are going to use the right-hand rule, this one, to form the mnemonics of this right-hand rule, first you have to make an L shape with the thumb and first two fingers of your right hand. Then, point your middle finger perpendicular to your thumb and index finger, just like this one. So that will be the right hand rule. So that would be all for this session. Thank you for watching. Thank you for listening.